Now that the information revolution is here to stay, another revolution is standing in wait at the door.
Everybody's interested in genetic engineering now.
CRISPR is a technology that enables us to totally rewrite the genetic material of plants, humans, and animals.
With all these DNA technologies that allow to do precise gene surgery on our DNA, surely this is another era.
All you need to know about doing your CRISPR experiment.
Soon, cells will be precisely programmed.
Viruses can be reprogrammed. They're essentially software. Think of them as apps for your cell phone.
And coding with DNA will no longer be just for expensive laboratories, but also for home use.
Come check out where CRISPR kits are being made.
Printing medicines and changing your own genetics? Will this soon be possible?
My particular application is to write software that kills cancer cells.
We get tattoos and stuff like that. Why can't we, grow a tail or grow wings?
It loads a lot of responsibilities on the shoulders of everyone.
And I tell you, it gives me goosebumps because I know that a 20-year-old student at a university that is learning biotech today has all the power and technology at their fingertips from their dorm room as a major pharmaceutical company. That's a game changer.
This is Backlight. Welcome to the world of your programmable body.
Je hebt niet een goed beeld van je toekomst later. Je weet niet echt wat er gaat. Het kan heel goed gaan. Ik kan helemaal niks krijgen, maar ik kan ook in een rolstoel komen. Ik weet heel goed wat ik later wil worden en zo en dat. Maar je hebt niet echt een vooruitzicht wat je nog allemaal later kan en zo. Dus het is heel erg genieten van elke dag eigenlijk. En elke dag is er één, zeg maar. Oh jee, ik heb geen parachute. Ja, dat weet je dus niet. Ja, dan val ik dood, ja. Als je een parachute hebt, dan kan je nog parachute springen, maar die had ik dus niet, blijkbaar.
Ivan has the genetic muscular disease FSHD, which affects his facial, shoulder and arm muscles. A disease for which there is currently no cure.
Het is in principe hoe eerder het begint, hoe ernstiger het loopt. Dus, en hoe korter de chromosoom vaak, hoe ernstiger weer de ziekte. Ivan heeft een beetje pech hier. Hij is heel actief en dat is goed. Dat is al bewezen, dat bewegen is goed voor je. Maar wij hebben medicijn nodig. Binnen 10 jaar, dan komt het nog goed. Het is een beetje nu race tegen de klok. Wat gaat er gebeuren? Hij gaat achteruit of een medicijn komt.
Imagine if you possessed the tools with which mistakes in your DNA could be altered, and in so doing, you were able to cure almost all genetic diseases. Imagine having a technology with which you could literally rewrite the DNA from each and every organism. This might sound like science fiction, but thanks to this woman, it has now become a reality. She is one of the inventors of CRISPR-Cas9, a revolutionary copy and paste tool for DNA. She is French geneticist Manuel de Charpentier.
If I have to explain the tool to someone who's not in the science, it's really imagining a text with words and a software, a tool that allows to precisely replace one letter of the word by another letter, delete a word or a set of words, or replace also the words that have been deleted by other words. So it's really a text editing tool that works very precisely. And the technology does exactly this on our DNA and genome. It works a little bit like programmable scissors that can recognize a certain spot on the genomes of cells and organisms and modify the genome at will.
Nederland heeft een belangrijke rol gespeeld, of Wageningen heeft een belangrijke rol gespeeld, of mijn groep heeft een belangrijke rol gespeeld. Omdat wij toch als een van de eerste toch hele basale principes boven water hebben gekregen. En daar ben ik best wel een beetje trots op.
John van der Oost is a microbiologist who has spent his life researching bacteria. In around 2008, he was working on pieces of DNA in bacteria, the so-called CRISPRs. His work laid the basis for this new technology, enabling us to copy and paste DNA.
Het is geweldig om te zien dat dit nou eigenlijk gebruikt wordt door allerlei groepen in de hele wereld. Ja, dit is echt een revolutie in de biotechnologie. Dus dat betekent dat er echt vanaf nu dat het allemaal veel sneller en veel efficiënter kan. En dat is dus echt, dat maakt een heel groot verschil. En niet alleen in de biotechnologie, maar dus ook in de geneeskunde.
John has been really one of the earliest pioneer, really focusing on the CRISPR mechanism and trying to understand how really those molecular machineries, CRISPR, are working. For me, it was important because he organized the first CRISPR meeting in Europe that took place in fall 2010. And this was for me the opportunity to meet for the first time my colleagues who were working on CRISPR, which was very nice because I could present my data and I could have the first interactions with the scientists. And they were all quite amazed by what I was talking about, and it was a very nice feeling to have the opportunity to be congratulated by whom I called the pioneers of the CRISPR field, whom I didn't know. So it was very rewarding for me, and also the fact that I was welcomed in the community in a very nice way.
Charpentier developed this DNA copy and paste technology along with American Jennifer Doudna. They have been lavished with prizes during recent years, including the prestigious Japan Prize and the American Breakthrough Prize.
Ladies and gentlemen, Cameron Diaz and Dick Costello.
Okay, just to clear up any lingering confusion, I am not a scientist, but I am a woman who has fallen in love with science. And I am thrilled to be here tonight because I do know that the life sciences, explored brilliantly by many of you in this room, offers us the secrets to life.
The Breakthrough Prize is awarded to Emmanuel Charpentier and Jennifer Doudna.
It seems only a matter of time before they receive the Nobel Prize.
It's kind of surreal to receive the prize from Cameron, and I was just thinking, three powerful women, and I was just wondering whether you were Charlie. Okay, good.
I'm a geneticist.
Yeah.
And I always worked on bacteria, mostly. And when you work with bacteria, you know that the type of research that you're doing can lead to discovering mechanisms that could have a high potential to develop new anti-infectives, but that could have also a high potential into developing gene technologies, because this is where they come from the mechanisms of bacteria and viruses.
Just like humans, bacteria are also bothered by viruses. These viruses release DNA in bacteria, telling them to make more viruses. But bacteria have their own defense system against viruses. It's called CRISPR-Cas. It can recognize the DNA of viruses, enabling it to precisely dissect and destroy it. Charpentier's team investigated this system, and along with Doudna, they were able to create the DNA copy and paste system that is now known as CRISPR-Cas9, allowing the precise and accurate reprogramming of DNA not only in bacteria, but in any desired cell.
It's a technology that originates from evolution in bacteria. And what I like is that it allows to study the evolution of the world.
The interesting thing is, in fact, we use evolution to change evolution somehow.
Exactly. We exploit evolution to impact evolution and act on the evolution.
Toepassingen van het CRISPR-systeem die zijn heel breed. Wat je ermee kan is genome editing. En dat kan betekenen dat je het genoom van een bacterie verandert of van een gistcel. Nou, dan hebben we het vaak over biotechnologie. Dus om micro-organismen te gebruiken om bepaalde interessante producten te maken. Ja, dit is echt een revolutie in de biotechnologie. Dus dat betekent dat er echt vanaf nu dat het allemaal veel sneller en veel efficiënter kan. En dat is dus echt, dat maakt een heel groot verschil. En niet alleen in de biotechnologie, maar dus ook in de geneeskunde.
Wil je drinken?
Ja.
Pak maar die glasje.
Ivan's muscular disease is the result of an abnormality in the DNA located at the end of chromosome 4. As a result, a highly toxic substance is generated in his muscles, which slowly breaks down his arm, shoulder, and facial muscles. Unfortunately, there is no medicine available, but with CRISPR, this genetic disease may possibly be repaired.
Ja, dat klinkt gewoon eigenlijk heel erg science fictional. Maar als het werkt, dan biedt het dan kan hij in één keer eigenlijk genezen zijn van deze ziekte. Dat is veelbelovend en heel interessant. En dat is natuurlijk the age of science. Jij weet toch een beetje hoe dat zit? Wat doet hij?
Maar
Nou,
eigenlijk bijna niet.
nou, hij wil toch een chromosoom kniepen?
Ja.
Je weet hoe je ziekte ontstaan? Door de korte chromosoom.
Ja.
Nou, dat kunnen we hem vragen straks.
Ja.
Him is genetic researcher Niels Gijzen. Diana and Ivan visit the Hubrecht laboratory in Utrecht, the Netherlands, where Gijzen is attempting to find a solution for Ivan's muscle disease by using CRISPR-Cas to change his DNA.
Moeten wij niet de witte jasjes aan?
Nee,
hoeft niet.
hier nog geen jas aan.
Oké.
Dit is het moleculaire lab. Dus hier werken we met moleculen. En eigenlijk het meest belangrijke molecuul waarmee we hier werken is DNA. Dus hier kunnen we genen, dus dat zijn stukjes DNA die coderen voor een bepaald eiwit, kunnen we voorbereiden om later in cellen in te bouwen, zodat we dat gen kunnen bestuderen. En een van de genen waar we naar kijken is dat DUX4-gen, wat bij jou zo'n probleem geeft.
Je weet het toch?
Ja.
En dat staat in jouw spieren, staat dat gen aan, terwijl het eigenlijk uit moet staan. En juist omdat het aanstaat, worden je spieren steeds zwakker. Maar we doen ons best.
Wil je iets zien?
Zullen we even gaan kijken naar cellen?
Ja.
Wij hebben nu de hele makkelijke delen bij bio.
Wat zijn probleem is eigenlijk is dat in zijn spiercellen wordt een eiwit aangemaakt wat eigenlijk niet gemaakt zou moeten worden. En dat eiwit is heel erg giftig. Dus langzaam sterven zijn spiercellen in zijn gezicht en zijn hals en zijn schouders. En misschien later ook in andere delen van zijn lichaam af. Waardoor hij steeds zwakker wordt. En bijvoorbeeld ook een vrij starre gelaatsuitdrukking heeft. En moeite heeft om zijn emoties te tonen. Dus hij kan niet goed meer glimlachen. Dat gaat er mis.
En dan zie je ook nog bobbeltjes inderdaad, een beetje hele ronde dingen.
Ja.
Dat zijn cellen die zijn doodgegaan. Of cellen die aan het delen zijn.
Simpel gezegd proberen we met CRISPR-Cas ergens in het DNA een knip te maken, waardoor dat gen wat zo'n probleem geeft, dus dat giftige eiwit, eigenlijk weer uitgezet wordt. Met CRISPR-Cas kunnen we nu dingen die we een paar jaar geleden onmogelijk achten, om maar een voorbeeld te noemen, om cellen in het laboratorium genetisch aan te passen, zodat ze een bepaalde fout die we bijvoorbeeld in het DNA, die we in patiëntencellen zien, dat we die kunnen nabootsen in het lab. Zoiets was een paar jaar geleden een project waar een promovendus 4 jaar over deed. En dat is nu iets wat in 2 weken voor elkaar kan zijn. Dus het heeft een enorme versnelling opgeleverd van het onderzoek. En daardoor kunnen we veel meer te weten komen in een veel kortere tijd. Dus dat op zichzelf is al revolutionair.
Wat gaat dat betekenen dan, als je dat zo snel gaat?
Wat we zien is dat met iedere nieuwe technologie die wordt ontwikkeld, en in dit geval is het CRISPR-Cas, maar dat gaat ook over genoomsequencen, dus de DNA-volgorde kunnen bepalen, of hele andere technologieën waarmee je ineens dingen kunt zien die je voorheen nooit kon zien. Dat geeft vaak een enorme versnelling van kennis en daardoor ook weer een versnelling van de toepassingen uiteindelijk in de geneeskunde. Maar het gaat nog steeds een lange tijd duren voordat patiënten daar uiteindelijk de vruchten van gaan plukken. Want kijk, wat voor ons in het laboratorium succes betekent, dat is dat we gisteren iets niet konden en vandaag wel. Maar tussen die ontdekking waarbij wij staan te juichen en de verdere uitontwikkeling van zo'n technologie tot een werkelijk toepasbare therapie, daar zit soms nog 15, 20 jaar tussen.
In my opinion, the problem that we have developing medicines today is that it takes too long and it's too expensive. And so, because there's such a large investment of time and money to make any drug product, you can really go after only the largest diseases and largest disease groups.
CRISPR-Cas9 is just one of the many developments which are greatly expediting biometric research. Andrew Hessel is a synthetic biologist who has worked in the pharmaceutical industry for a number of years. But his greatest frustration is the pace at which new medicines are able to enter the market. So he decided to go his own way.
I wanted to hack the biopharma industry. And after I left the pharmaceutical world, I thought, well, what can a single individual do to really change the biopharma industry? I was unattached. I wasn't with a university organization. I didn't have a company at the time. So I had to think of some idea that would ultimately be big enough to change the world. I called it not big pharma, but big idea pharma.
One of the places Hessel worked for a while was at the software company Autodesk. This firm produces 3D design software. While there, Hessel was occupied with the digital design of biological systems.
The world of computers and biotech are really closely related. In terms of just architecture, the cellular architecture and the architecture of our bodies actually is very close to the architectures we've created in computers. You can look at the cell as a computing device and a manufacturing device. It's like a smart 3D printer, and the DNA of that cell, which manufactures that cell and runs the operations, actually dictates the construction of thousands of different components. So it's like a really smart, really powerful, really programmable 3D printer. Once you understand the architectures and start to digitize the processes, you realize you can go and make a digital biology that's quite accessible and very, very powerful in terms of manufacturing.
Slowly, we are beginning to control DNA, the genetic code of life. DNA is comprised of 4 substances designated by the letters A, C, T, and G. The sequence of these substances determines the genetic code of a cell. With CRISPR, we can now accurately read and write with these 4 substances, and thus reprogram the cell. But this is still not enough, according to Hessel.
In terms of programming, we're still down working with the bits. In biology, it's A's, T's, G's, and C's. In computing, it's ones and zeros. We're working at the bit level most of the time to assemble the code. That is extremely hard. But what we've been seeing over the last 10 or 15 years as synthetic biology, the field has come into play, is we've started to modularize the instructions. We're saying this little bit of A's, T's, G's, and C's is a switch to turn a gene on. So now we just call it a switch, and then we build another system that is, a reporter. And here, so we start to functionalize these code blocks, and now those code blocks have the genetic code encapsulated in them. You never have to look at them. And once you've done that, now you can start to assemble those code blocks and say, here's a switch, here's a sensor, here's a reporting device, and you just drag and drop the components to build a new circuit. So now it becomes accessible to someone who isn't a biologist. Now someone that is familiar with even wiring a simple electrical circuit can now build a simple biological circuit. And that's why we're starting to see kids, literally 7, 8 years old, starting to build their first biological constructs.
Josiah Zayner may no longer be a kid, though he may sometimes behave like one. But he is a real biohacker. He sells CRISPR kits on the internet to anyone who wants one. He once worked for NASA, but found it too bureaucratic. His living room has now been transformed into a packing division for biomedical items.
Hey everybody, we're here at the Odin in West Oakland, California. Come check out where CRISPR kits are being made. Over here, starting and left back, we have Alan making the media. Micah. How's it going? Peter. And this is the kits we make and we ship out to people. So our kits come with everything people need to do CRISPR experiments. You don't need anything, no experience at all. So I grew up in like the late 90s when there was like this whole computer hacker type culture, right? Where it was like, you learn how to do some cool stuff and then manipulate technology to get it to do what you want to do. Well, I saw that like biology is this interesting technology and maybe different aspects of biology can be kind of hacked. This idea of like a biohacker as opposed to say a computer hacker started to be born in my mind. And I started to try to develop ideas and experiments along this line. And I thought, well, maybe I could make a kit and get that in the hands of people to show them how to use this technology. And then people, you know, got really excited by CRISPR. I think the coolest thing about CRISPR is not necessarily like all the genes it can edit and all the things like this. It's that like everybody's interested in genetic engineering now, right? Even people who are like anti-GMO or like didn't like GMOs, now those people are interested in genetic engineering because of CRISPR.
Zayner experimented with CRISPR on himself. He attempted to make his muscles grow more quickly. The attempt failed, but his enthusiasm only grew.
My dream is that it becomes like more open, people become more open to human beings changing their own genetics as adults or as children, change the way we think about being human. Instead of just everybody being born with the genetics they have for their whole life, maybe we can start changing that up. And for interesting and fun stuff, you know, everything doesn't have to be, everybody, you know, cure this disease, cure that disease, you know? It's like, you know, we get tattoos and stuff like that. Why can't we, you know, grow a tail or grow wings or, you know how much scientific research has gone into like growing a tail in human beings? Probably like none. But like a lot of people probably think that's pretty cool. Companies can do that if this technology opens up. Or like growing wings. Who knows if that's even possible? Probably not. But nobody's trying, right? Or like different things, you know, changing your hair color or skin color, growing more hair or less hair, or, you know, there's so many opportunities for this technology to be more than just, you know, another medical treatment or another, you know, technology that only big pharmaceutical companies own. We think that genetic engineering is such a powerful technology that it should be accessible to everybody. So, in effect, nobody owns CRISPR and everybody does, right? It's kind of like, you know, any sort of knowledge. Like, it's like saying who owns knowledge. I mean, some of the academic publishers might say they do and charge you $100 to read a scientific paper, right? But in effect, you know, knowledge isn't owned.
Zayner and Hessel both have the same goal, making biotechnology accessible to everyone. Zayner does this with his CRISPR kits, and Andrew Hessel through making biology digital.
My whole goal was to bring the tools of biology into the digital world, digitize them as much as possible, make them automate, make them accessible via computing, and put an open source business foundation around it so that we can share information and ultimately build a community that can work like the pharma companies.
With digitizing biology, Hessel means creating on the computer viruses containing DNA which could then be utilized, for instance, to help fight cancer.
Viruses are really interesting biological agents. I do not consider them to be alive. I consider them to be software. And you can, if you buy a software program, it is not alive unless you load it on, it does not operate unless you load it onto a computer. So a virus by itself is a bit of protein and a bit of nucleic acid, either RNA or DNA, that you can think of as almost like a floppy disk if you're my age, or a memory stick today if you're modern. It is a program loaded into a physical structure. That physical structure will dock with a cell and load the program into the cell. And now most of the time the program is make more viruses. But we've gotten very good at engineering viruses to deliver programs that we think are interesting into the cell. Either make this protein because it's a good drug, or we can load a program into a cancer cell that says die. So viruses can be reprogrammed. They're essentially software. Think of them as apps for your cell phone. But we have this opportunity now to start to design viruses from scratch. It is a way of making programs for biology that can then do useful things. So the virus is simply the way to load software into cells and add new applications. My particular application is to write software that kills cancer cells.
All tumors are different, and with his new company, Humane Genomics, Hessel wants to create cancer-fighting viruses in which the DNA is precisely directed at the tumor it must fight. Special DNA printers will be able to print this specific DNA and place it in viruses. In this way, everyone will have access to personalized cancer medication.
And now we've partnered with a group in Alabama at Auburn University that has a veterinary school and research center to make cancer-fighting viruses for dogs. They had done some pioneering work with genetically engineered viruses, oncolytic viruses for dogs. I met a doctor there by the name of Dr. Bruce Smith and said, let's upgrade your technology. Let's go into the world of digital design of viruses. And so last year, in 2016, we made the world's first synthetic cancer-fighting virus for dogs. You know, we've only built one synthetic cancer-fighting virus. This year, Humane Genomics will make about 10 viruses and treat 10 dogs. We already get personalized trainers, personalized diet, you can get personalized clothing. I believe more and more of our medicines and medicines that keep us healthy, think of them as vitamins, should be personalized as well. And eventually I can see having an EpiPen type device that has essentially a pharmaceutical company inside the device. And the doctor can upload your medicine into that device, and it just goes beep when it's ready, and you do an auto-inject. So that's the future. How long it takes to get there, really depends on our will. But there is nothing science fiction in that process today. We're already seeing the miniaturization of all this equipment. The design tools already exist in the cloud, and ultimately single-use injectables are used all the time with things like EpiPens.
Hessel suggests that for around $100, you'll be able to get a kind of medical Netflix subscription to keep your DNA healthy. These are now only ideas, and Hessel's company is just getting started. But fiddling with our DNA is already becoming commonplace. Reading your own DNA, DNA analysis, designing and printing DNA codes, copy and pasting DNA using CRISPR. It's all becoming cheaper, more accurate, and easier as child's play.
And we got the bacteria in these little vials. They're hard to see because they're bacteria, you know.
What kind of bacteria?
Really tiny.
What kind is it?
These are special strains of just lab E. coli, non-harmful, non-hazardous, non-pathogenic. They can't cause disease or anything.
And the DNA, where does it come from?
We actually get it synthesized from companies and then put it in these little tubes. So you can see it frozen in there. Frozen DNA. So a lot of these things are very science specific and really expensive if you actually bought them, you know, from normal companies. So we got, this holds tubes. We got pipettes. So pipettes are basically devices that allow you to move around small amounts of liquid. They suck up and move around liquid. Every scientist needs one. We got tips for that. You need chemicals to help get the DNA inside the organism. And then we need the DNA, put these in the kit, the guide. All you need to know about doing your CRISPR experiment.
And where is it going?
This one is going to the VAG in the Netherlands.
Experimenting with DNA in a backroom or garage. It's reminiscent of developments in the 80s when Bill Gates and Steve Jobs were playing around with computers. But playing with DNA is different from playing with computers. The CRISPR technology has travelled widely during recent years. Experiments with gene alteration are now going on a global scale, and experiments with the genes of embryos.
A number of countries have already started to apply the technology for research purposes on human embryonic cells, so at a very early stage, so really a few number of cells to allow to understand the early mechanisms of life. That can be also interesting to understand because there are certain diseases that develop very early on. Now, the idea to use the technology for human embryos or human germlines for the purpose of modifying the genome for after reimplantation in the human bodies, it's another story. So for sure here there are strong ethical issues.
Yeah, because that's one of the concerns of a lot of people.
This is one of the concern, is that the technology will be used beyond its initial purpose, that is to treat human patients.
But it loads a lot of responsibility on your shoulders.
It loads a lot of responsibilities on the shoulders of everyone, I will say, because then specifically scientists, developers and clinicians have a role in making sure that the right regulations are in place and that the technology is correctly used for the purpose, at least for medicine, which is to cure patients.
In the VAG in Amsterdam, the boundaries of art, science and technology are being explored. It's also where a Biohack Academy, a do-it-yourself lab for biotechnology, is being organised. Anyone who so desires can be inducted into the world of biomaterials and the cultivation of microorganisms.
Oh, that's it, the CRISPR kit.
On the basic CRISPR course, they're learning how to play with DNA.
All right, so there's tubes, there's gloves, and then here's the thing that actually is the most important, the little tubes. They're also really cold. So here's the RNA we're gonna add and the transformation buffer and the plasmids. So how much do you think it is?
It sounds fantastic. We can all now play with our genes using the CRISPR technology. But if we really want to create medicine, the business aspect of it will soon be peeking round the corner. There is a real patent war taking place for the rights to the various aspects of the CRISPR technology. In Boston, this all comes together.
Boston is een geweldige plek. Dat is echt een hotspot. Dus je hebt MIT, je hebt Harvard en dan al die instituten eromheen, zoals het Broad Instituut. Daar is heel veel geld, daar zitten hele goede mensen. Dus dat is echt het neusje van de zalm.
John van der Oost has the patent on a component which can be used with CRISPR, and he travels as an advisor to various businesses in Boston, also possessing component patents.
Ik ben in Boston om een aantal mensen te bezoeken. Ik ben uitgenodigd door Fong Zheng van MIT Broad en door Keith Young van Harvard Medical School om daar een verhaal te houden. Dus dat gaan we doen. En verder ga ik zo meteen langs bij Editas. Daar ben ik al vaker langs geweest en die maken veel gebruik van CAS 9, maar ook van CAS 12 of CPF1. En voor hun toepassingen. Dus, en dan gaan we praten over de voortgang van het onderzoek bij ons, voortgang van hun eigen onderzoek. En ik ben ook wel benieuwd of er weer mogelijkheden zijn om de banden aan te halen en verder samen te werken.
But no one is willing to reveal all. Even van der Oost doesn't always know what the companies are working on.
Er zijn inmiddels een groot aantal bedrijven begonnen om de CRISPR-technologie te gebruiken om humane ziektes aan te pakken. En ik weet niet waar al die bedrijven mee bezig zijn. En dat vertellen ze ook niet altijd. Maar als je bijvoorbeeld het bedrijf hier in Boston, Editas, als je daar op de website kijkt, dan zie je dat ze bijvoorbeeld zich richten op de oog, op bloed, op kanker en op de lever. Like structures. And then the other class 2 systems, and at the end then you get unwinding of this part and then swinging in of the target strand. En natuurlijk willen ze daar op een gegeven moment ook geld aan verdienen, maar dat zal elk bedrijf willen. Dus die halen regelmatig geld op en dan, ik bedoel, daarom kunnen ze nu eigenlijk een team van al bijna 100 mensen hebben ze op de been gebracht. En dat kan natuurlijk alleen maar met extern geld.
Heb je enig idee hoeveel geld?
Ik heb geen idee hoeveel geld, maar je leest wel eens op internet dat ze weer een succesvolle ronde hebben gehad. En dan hebben we het over rondes van $100 miljoen. Dus dat is aanzienlijk.
Hi. Welcome to the road.
The new companies Editas, Caribou and CRISPR Therapeutics are all owned by people who were present during the development of CRISPR. It's estimated that with CRISPR, over 3,000 genetic diseases could be cured. If this can be realized, it would result in a tremendously large market. Each of these new companies would have the potential of becoming the new Google.
Nou, die kans is groot dat die bedrijven inderdaad enorm veel gaan betekenen. En natuurlijk wat Apple en Google in de bioinformatica of in de informatica voor elkaar hebben gekregen. Dat zijn nu bedrijven als Editas en Caribou, maar er zijn er nog wel een paar, die zijn nu enorm aan de weg aan het timmeren om ook in de biologie heel belangrijk werk voor elkaar te krijgen. En dus eigenlijk de hele technologie naar de markt te brengen.
En is er dan het gevaar dat ze te veel macht krijgen, zoals Apple en Google?
Ja, dat zou ik eigenlijk niet durven zeggen. Misschien, het is sowieso goed om dat heel goed in de gaten te houden. Maar dat moet met regelgeving afgebakend worden wat wel en niet gewenst is.
The biohackers in the VAR still have greater concerns than just the patents. It may now be easy to play with genes, but if you're really going to alter your genes, there will be problems to confront.
Okay, so now we're at the last step of the protocol. First, we'll discuss some more the societal issues around CRISPR, and then we come to the last part, which is, are we going to do it? Are we going to heat shock the cells or not?
The biohackers are nearly ready. The original idea was to use CRISPR to make bacteria resistant to an antibiotic. The latest step is to use CRISPR to give the protein in bacteria a heat shock, as only then will the genes of the bacteria be altered. But in the Netherlands, you can't just alter the genetics of an organism.
But for this CRISPR kit, we actually don't have the license. So when we do the heat bath, it would be illegal from that perspective.
But punishable by what?
In jail?
I think this is a bit of a gray area. I don't know. It's also something that's not been tested a lot, I guess. At least I haven't heard of it. Because of course it might be that people do this in their garages or kitchens and have used this kit also in Holland, because we could order it with not a lot of trouble. I mean, the douane, the border control didn't pick it out. But then the whole thing about Waag Society is we try to make it transparent. So, I mean, it's even videotaped. So this means it's a different situation. So that's good, of course, because this way we make it debatable. I don't know how illegal. I mean, it's illegal. It's 100% illegal.
If something happens, you don't know what will happen because we are not trained as. I mean, you are of course trained, but we are not trained as biochemists, so we don't know what we should do then. I'm not sure if we can do it with that amount of knowledge. Yeah.
But the actual, because it goes further than just editing it to be resistant to antibiotics. So you can go way further. And I think that this could be the beginning of, well, it is already the beginning of editing something that's in a much larger picture. And that's the question, not only if to make this part now what we're doing at Waag.
Yeah. So the question is, are we going to do it or not?
With all these DNA technologies that allow to read the DNA, that allow to do precise gene surgery on our DNA, surely this is another era.
But you can't control, let's say, the effect of this technology globally.
No, the critical aspect of any technology that is developing, such as CRISPR-Cas9, is that, first of all, different countries have different regulations in terms of biological ethics. And this is the case for CRISPR-Cas9, so different countries have different views with regard to how far one can go to apply CRISPR-Cas9, for example, in humans. And it will be difficult to get to a general consensus because of different types of cultures and different ways regulations are already in place.
And different, let's say, ethical ideas.
Yeah, in
different cultures. So.
Indeed. So the different cultures, the different ethical regulations already in place, surely we will bring that it will be extremely difficult to have a consensus on certain applications globally.
All right, I think we should have a vote. So the heat bath is here, it's at 60 degrees. The next step in the protocol is heat shock. Who would do it? I mean, I want to see hands. Then we won't.
You have to understand though, like, people are scared of a lot of technology these days. Artificial intelligence, right? It's going to destroy the world. Genetic engineering and CRISPR, it's going to destroy the world. Honestly, if like the printing press was invented today, they probably wouldn't let anybody use it because it would destroy the world, right? And if you go back in time and say, what has caused the most damage out of any technology, you might say it's the written word, right? Like, wow, look how much damage has been caused, but look how much beauty has come because of it. Same thing with like cars and automobiles, right? Every year, millions of people die in automobile accidents, and we're all okay with it because it brings us so much in our lives, being able to travel long distances in very short periods of time. And I think it's the same way with these genetic engineering technologies like CRISPR. Obviously, everything can be used for bad, right? Bad stuff can happen from. But what's the possible benefit of this, right? What's the possible benefit? And the benefits are, really immense.
We've done the groundwork with biology and digitizing it. You can go to digital libraries of information. There's gene banks of information. There are now databases of synthetic biology tools and processes. There is a digital architecture where I can now get online researchers and tools and equipment and services. And soon, we're just starting to get the acceleration now. We're just hitting the knee of the curve where this is becoming, where there's a large enough community, the tools are cheap enough and accessible enough and connected enough to really start to accelerate. And I tell you, it gives me goosebumps because I know that a 20-year-old student at a university that is learning biotech today has all the power and technology at their fingertips from their dorm room as a major pharmaceutical company with just a little bit of funding. And that's a game changer. So we are going to see an incredible acceleration over the next generation that will be surprising to many people.
Maar wanneer?
Wanneer? Dat is een hele
Wanneer wordt hij
belangrijke vraag.
gerepareerd?
Nou ja, dat is ook zo moeilijk aan het voorspellen van hoe lang gaat het
wanneer
duren.
de ontdekking?
Er zijn bepaalde ontdekkingen gedaan waarbij mensen dachten van nou dit gaat nog jaren duren en dan ineens kan het. Aan de andere kant lijken sommige processen ook zo van nou nog een paar stappen en dan zijn we er. En dan lukt het maar niet.
Nee. Of moet je opnieuw
dus
beginnen?
het valt heel erg moeilijk te voorspellen.
Nee. Nou laten we hopen.
Ja, dat zeker.
Hard werken.
Ja. We doen ons best.
Wil jij nog iets weten?
Nee, ik weet alles.
Je weet alles? Ah, goed. Nou,
Nee, ik weet
we
niet
hebben
alles,
iemand die
maar-
weet alles.
Ich hoffe, dass Ihnen das Video gefallen hat. Klicken Sie hier, um das empfohlene Video anzusehen. Bitte abonnieren Sie unseren Kanal, um Updates über VPRO-Doc zu erhalten.
Where's the fourth one?